Good afternoon, everybody. It is great to see how many of you have joined us here today, and welcome to this webinar hosted today by Semblex. The speaker today is Dr. Brandt Ruszkiewicz, Product Development Manager at Semblex Corporation. Brandt is the Product Development Manager at Semblex, a fastening supplier in Chicago, Illinois. Brandt is tasked with developing new fasteners and joining technologies to meet the needs of our customers, as well as the development and implementation of new manufacturing technologies to increase process control and quality. Brandt has a PhD in automotive engineering from Clemson University International Center for Automotive Research and a bachelor's degree in mechanical engineering from Penn State. We do encourage you to ask plenty of questions at any point during the webinar. Please type in your questions into the Q&A box you will find at the bottom of the screen. At the end of the presentation, we will present your questions and answer as many as possible. It is a pleasure to have Brandt with us today, and I would like to warmly welcome him now to take control and begin the session.
Thank you, and thank you everybody for participating today and coming to watch and learn about Rolok HS. Rolok HS is Semblex's new thread forming fastener for high-strength steels. Today we're going to talk about where the fastener came from, what are some of the challenges it solves, and what are some of the potential applications. But I'd like to start with looking at what the problem is. So on this video to the right, you're going to see a traditional thread rolling fastener, one of the most popular ones on the market, at least here in the United States, trying to drive into 3mm thick HSLA 550. HSLA 550 has a tensile strength of around 620 megapascals, and one of our customers came to us with this application telling us that periodically they would have screws that just wouldn't drive into this material. Or if they pushed really hard on the screw, it would drive through the part. Now they noticed that this failure was intermittent, and they eventually linked this back to their punch presses. So when their tooling started to wear, they started to have issues with these parts driving in. Upon some closer inspection, they found that when the tool started to wear, the interface hardness right at the edge of that hole got very high, and this caused some of the fasteners to start to deform. So in this video, if we look to the pictures on the left, this part with a little bit of damage down here on the first couple threads, that's from this video, and that's what the customer was seeing whenever the part wouldn't drive in. Now, if they pushed really hard and forced the part through, they would essentially destroy the threads the entire way up the length of the fastener. And you can see this in this picture right here. Obviously, this wasn't ideal, so they asked us to find a solution for this and some other potential problems. So in order to do that and to better understand Rolok HS, we're going to start with the basics of thread rolling fasteners, talk about some of the challenges they face in these higher strength materials, and try to understand why they're failing. And then we're going to look at Rolok HS, which is a new design. We're going to look at how it overcomes some of these challenges that our traditional fasteners are facing. We're going to look at some validation testing across 3 different materials, showing a big strength range that Rolok HS will work in, and then we'll go through a brief summary. So to make sure that we're all on the same page and we all understand what we're talking about, we're going to start with the basics of thread rolling screws. So a thread rolling screw is simply a fastener which roll forms its own mating thread into a nut member. The benefits here are that we don't generate any chips, we're not cutting, we're forming threads. However, you do need to have a pre-hole in your part that is sized correctly for the fastener that you want to use. All thread rolling screws have at least these 3 basic attributes. One is that they have a tapered lead, and this is what separates them from traditional machine screws. So if we look at this picture on the bottom left, you can see where all of these thread crests are the same height, and then they start to taper down. This is the tapered lead area. This allows these screws to slowly form threads into the part, enabling a nice clean thread formation. All of these fasteners will typically have some type of torque controlling feature, and we'll talk more about that on the next slide. Now finally, and the one that's important for this presentation, your fastener has to be harder than the mating material. But what happens when it's not? Or what happens when that mating material starts to get close to the same hardness or the same strength as your fastener? That's when we start to see some problems, such as what you saw in the video on the last slide, and that's what we're designing Rolok HS to do, is to overcome when that happens. Now, torque controlling features are very important for thread rolling fasteners. If we look at this graph on the left, this is a drive to failure curve, so this is what we run whenever we want to figure out what tightening torques we can use on an assembly line. We look at this curve, we see two different peaks. The first peak here is what we call the drive torque. This is the torque it takes to form threads into your material. Once you've reached this top torque value, you form threads all the way through your part. After that, you're simply just running the screw down until the head touches, which is right here. Once that head touches, your fastener starts to stretch, you start to generate clamp, and then if you go too far, something breaks. That could be the female part strips, the fastener breaks, or the fastener thread strip off. Now we want a very large gap between these two peaks if possible, because we need to tighten to somewhere between these. If we tighten to less than the drive torque, then the fastener hasn't seated yet. If we tighten too high, then we risk breaking the joint. The bigger the range here, the better, and there's some different ways that we can control that, and that's where these torque controlling features come in. If we look at the second image here, this is what's called a non-round body. If we look at the cross section, we see there's 3 contact points. This is called a tri-round fastener. Commercially, this is the Tap-Tite family of products, which is one of the most popular thread forming fasteners on the market. These work very similar to conventional taps. So if you've ever used a tap to thread a hole, you'll notice that you have a threaded region followed by a relief area where there's no threads or no material. So that what you're doing is you're cutting and then you're following it with a relief, and that keeps your torque down and makes it easy for you to use that tap. These fasteners work the same way. You have these points up here, and that's where you're doing most of your thread forming, and then behind that you have a relief to reduce the amount of torque. There are different ways to do this. For example, we have the spiral lobe one to the right of the tri-round. This one's still a round body, but it has these little lobes that protrude at 3 different areas to separate your relief from your forming. You can have combination designs that combine these 2 features or some others, or you have some fasteners that concentrate only on the thread forming point, which is in your tapered lead region. Now, most traditional thread rolling fasteners have a 60-degree flank angle, and it's very important for what we're going to do with Rolok HS. The 60-degree flank angle is simply the angle between the thread faces. It's the same as a standard machine screw, which is where these thread rolling screws came from. However, as we saw in that video at the beginning, some of these fasteners just don't work when that steel starts to get hardened, whether that be from manufacturing operations or just from the steel being high strength on its own. So to look into this further, we looked at simulating a screw that was only a little bit stronger than the material it went into to see if we could duplicate what we saw in that video at the beginning. So in this video that I'm going to play to the right, we have a 60-degree conventional thread rolling screw. It's an equivalent class 10.9, which means it has a tensile strength of about 1,000 megapascals. It's going to go into this blue material here, which is DP800 steel, which has a tensile strength of 800 megapascals. Now, when this screw tries to form threads in this material, you can see the threads, they bend and then they collapse. And this female thread that's left behind is not very well formed, but if you look at this screw, it looks a lot like this picture at the bottom, which is similar to the one we showed earlier, where when those threads fail, they bend and then they collapse down, and it almost looks like you just took the tops of the threads off. What you actually did is you just bent it and collapsed it. Now, to overcome this, I'm often asked, well, why don't you just make the fastener stronger? Why don't you make it harder? And we can certainly do that, but there's some prices to pay. If to get there, we have to change the alloy of our fastener or change the heat treatment, or maybe both. That can add quite a bit of cost. In addition, when you get into these harder, higher strength fasteners, you tend to have an increased risk for hydrogen embrittlement, especially if you're going to use an electroplating with it. And then finally, the higher strength fasteners tend to have less ductility and less fracture toughness, which can be an issue if it's a safety critical application, especially if it's a seat bolt and that really can't fail in a crash scenario. So if we want to make a fastener that can go into these high strength steels, but we don't want to change the heat treatment, what do? Well, if you remember, I said most traditional thread rolling fasteners had a 60-degree thread flank. So maybe that's the problem, and that's what we looked at when we developed Rolok HS. On the left side of the screen, you can see a depiction of a traditional thread rolling fastener's flank, which, as mentioned, is 60 degrees. Below that, we see Rolok HS. Rolok HS's thread design is what's known as a compound flank angle, meaning there is more than one set of angles on this thread. In this case, there's two. So this upper angle here is very wide. So what that does is it changes the loading on the fastener. So with a traditional 60-degree flank angle fastener, we have a lot of the load that goes into trying to bend this part, tries to bend that fastener, bend that thread, and that's what you saw in the simulation on the previous slide. With Rolok HS, we switch that bending load to more of a compressive load. So rather than trying to bend this thread, we're trying to compress it. And there's some key differences there. Obviously, if I bend this thread, once it's deformed, it's not in the same shape anymore. And you saw that in the simulation video on the last slide. But when I try to compress this thread, it's actually going to stay in the same shape even if it deforms. It'll just be a little bit shorter. Underneath that large flank angle, we have a much narrower flank angle. And what that lets us do is stay serviceable with standard machine screws. All that actually means is the pitch and our diameters of our Rolok HS screw match a standard metric machine screw. So if you form a thread with an M5 Rolok HS and you take the Rolok HS out, you can insert an M5 metric screw in its place and it'll work just fine. Finally, is our torque controlling feature to make sure we have a good gap between that drive torque and the failure torque. We chose to use the Rolok spiral lobes, which is where the Rolok HS name comes from. It simply is Rolok for high-strength steels. The reason we went with the Rolok spirals instead of a trilobular body or a non-uniform cross-section is that we get better stripping torque performance out of a round body fastener. That was going to be very important for these high-strength steels. So once we finished the design, we went back to that simulation where that you already saw, and we subbed out the fastener, and this time we ran it with the Rolok HS design. So you're first going to see a repeat of the traditional fastener where it bends. Following that, you're going to see an equivalent class 10.9, the same as what we use for the standard fastener, drive into the DP800 steel. It's going to change over here in a second, and you'll see the Rolok HS thread form sitting up here. It almost looks round when it's zoomed out, but when this starts to go in, you'll notice, if you look very closely, these flanks are actually compressing slightly, and they're becoming a little bit more round. But our female thread ends up looking just like the Rolok HS thread, even though we had some deformation. Very different from what we see with this traditional thread forming fastener, where the female thread at the end looks nothing like the original cross-section of this part. And I'll leave it up to let it run through one more round of Rolok HS. If you look at the thread before up here, and then if you look at the thread in the female part afterwards, they're going to look almost the same. That's exactly what we want. That means we're going to be able to get a good joint. We're going to get good performance. On the bottom, you can see stress plot, and that's basically where we're looking at some of the material flows into our thread to make sure we're getting good engagement and a good flow out of this material. Now, as far as heat treatment goes, as mentioned, we're trying not to change these. So we're still using the traditional heat treatments you'll have on thread rolling fasteners. We recommend a case hardening for anything that's not safety critical and anywhere where your mating material is less than or right around 800 megapascals. For everything else, we recommend induction. We're also playing with a new heat treatment called OS tempering, and we'll talk about that later on. That's for very specific, very high-strength applications. So going back to this original customer problem where the traditional thread rolling fastener wasn't working, and what we originally tried to solve with Rolok HS, we can see that on the left we have that same video you saw earlier, but on the right we're now driving Rolok HS in, and it's actually the same plate. If you notice these X's that I keep drawing on here, if you look over to the right screen, you'll see those same X's, and we'll actually take Rolok HS and drive it straight through those same holes to show that it's the same plate. There's no tricks here. We're using this screw, it's going through this material. In this case, both screws are case hardened because the steel is only 620 megapascals. We don't need induction for this. We're spinning them both at 225 RPM, and we're going all the way to failure. On the top left, you can see the thread rolling progression and how we form threads into that part to get the final Rolok HS geometry. And on the next slide, we're going to show a bunch of data for this. So obviously, our customer wanted a solution, so they definitely wanted the data to go with that solution before they went to their own plant trial. So to do that, we had to do a couple tricks. The Rolok HS part was able to drive in with 10 pounds of end load, but in order to get drive to fail curves for the other part, I needed to push very hard on the fastener. So what we did is for the competitor, we increased the end load to about 40 pounds, and that was enough to push the part through. But as you saw in those earlier pictures, we do a lot of damage to the threads when that happens. Now over here to the left, we mentioned that they were having issues when their punches started to wear. So on the left, we have a new punch with a nice sharp edge. On the right, we have a punch that we took to the grinder and took the edge completely off. This simulated our worn punch and is much worse than what we typically see from any of our customers. There's two pictures of a hole to the right of that. These are from the worn punch. The top picture is the punch entry side, so that's where the punch initially contacted the steel. The bottom is the punch exit, and you can see how nasty this looks. It's very blown out. There's actually a lot of cold working in here, and it's going to be very hard at this interface. This is the side of the joint that we drove the screws through because that's where our customer was having the problems. Now you're going to see some comparison data here. If you remember that curve early on, that first low peak, our drive torque, is the light blue bar. That higher peak, that failure torque, is the dark blue bar. Now we tested across a hole size range, and this was the tolerance on the hole given to us by our customer. So for thread rolling screws, you're going to have a higher drive torque when the hole is smaller because you need to move more material. So what that means is that these light blue bars, these drive torque numbers, come from the small hole size. But whenever you go to fail the joint, in this case it was the female threads that were stripping, the larger the hole size, the less contact you have, so the lower your strip torque. So our failure or our strip torque, the dark blue bar, is coming from the larger hole size. So essentially, we're showing the data across the entire range in the worst case scenario. So we have the highest drive torque with the lowest failure torque that you're going to see from this application. If we look at the competitor, remember we want a nice big gap between that drive torque and that failure torque. But in order to account for variability, we typically add 3 standard deviations on the mean, and that's what these error bars represent. So our upper drive torque limit is basically right up here on the top of this error bar. Our lower failure torque limit is at the bottom. We want there to be a gap between these. Because if I take this part and let's say I tighten the 5 Newton meters, well, I'm overlapping this bar here. That means that I could have a fastener that hits our 5 Newton meter tightening torque without the head ever touching. On the other side, that could also mean that because my 5 Newton meter overlaps inside this failure range, I could go to 5 Newton meters and strip the joint, which isn't good. You're going to have to scrap that part or do some type of repair work. When we look at Rolok HS's bars, we see that from the upper drive torque limit, which is about 4.5 Newton meters, all the way up to the lower failure torque limit at about 8 Newton meters, we're good. Any torque in that range will work pretty well. Obviously, we would recommend something in the middle because we will have some variability from the tolerances on our platings and our heat treatments and the fastener itself. After seeing how well Rolok HS was able to work in this damaged HSLA 550, we wanted to see how high strength we could go. So one of our other customers came to us with an interesting application. They had 2 millimeter thick DP980 steel. They were trying to use a traditional thread rolling screw, which is labeled as the T on this piece of steel over here, and you can see what was happening. They were completely wiping the threads off their part. They had to push very hard to get these parts to go through the steel, which was causing some ergonomic concerns for their operators. Next to that, you can see Rolok HS, so obviously spoiler is it works. The conventional screw didn't work at all. Our customer was actually going to move to a rivet if we didn't give them a fastener that worked better. And that's where Rolok HS came through, and that's what they're currently trialing in their plant. But one of their questions was, do we do case hardened or do we do induction hardened? Obviously, case hardened is cheaper than induction, so if you can get away with case hardened, it certainly works well. So we ran both sets of data and left it up to our customer to decide. So if we look at the case hardened part, we see that we actually have a pretty good window for installation. Once again, we're on a hole size range, so the lower bar is our small hole size. The larger failure torque bar is our large hole size. And we've got a range anywhere from about 3.5 to 7 Newton meters with the case hardened part. But when we compare this to the induction, we see a much bigger window, and there's a couple reasons for that. If you remember that simulation early on, Rolok HS can still deform. It will still drive through even if it deforms. We're simply going to end up shortening and crushing that thread a little bit. And we see that show up as a higher drive torque with higher variance. Obviously, the error bars here are larger, telling us there's more variation than what we got with the induction hardened part. Because those threads got deformed a little bit, we end up with a lower failure torque on the case hardened part than what we have on the induction hardened, which gives us this very large installation window, which works very well. After seeing how well Rolok HS was able to work on DP980, we wanted to go up one more level, go up to something brand new and very strong. So we went to a Generation 3 quench and partition steel, and you'll see the video of us actually driving Rolok HS into that part. So this stuff, brand new, just came out a few years ago, just getting its way into the automotive industry. Here we're going to run induction hardened parts because 1200 is simply too high for a case hardened part. But because this steel is thin, we had to flow drill an extrusion, which you can see in this picture on the top left, to give us enough length of engagement for our M5 screw. So the steel is only 1.2 millimeters thick, so we used a carbide flow drill, which is a separate operation. The screw does not make this extrusion. And then we drove the screws into that extruded hole. We did check the hardness before and after, and we were within 2 points of the original on the Rockwell C scale, so we still had about the same strength, right around 1200. So for this, we did actually test a competitor's screw. It's not shown in the video, but you'll see the data on the next page. And the reason why we didn't show it is because the data is more or less non-existent. So if we look at the competitor's screw, once again looking at a hole size range, we see that the drive torque and the failure torque are actually about the same number. I mean, they are the same number statistically. And what that tells us is that we actually didn't form any threads into the steel. So if you remember that simulation early on, even though those threads collapsed on the traditional thread rolling screw, it still did form a little bit into that steel. But on this 1200 steel, it didn't form in at all. We flattened out all the thread crests, bent them and collapsed them, never formed any threads into the steel, which is why our drive and our strip torques are exactly the same. We look at this curve on the left. If you remember early on, we showed a drive to failure curve where you had that nice low peak and that nice high peak. Yeah, you don't get that with a traditional thread rolling fastener in this steel. Our drive torque and our strip torques are about the same. When we transition over to Rolok HS, we do see a window across the hole size range. It's not as large as we would like, but that's why we're starting to look at some other heat treatments. So what's interesting is actually in this steel, our drive torque's pretty good. I mean, it's almost the same as it was in DP980. So our DP980 was about 2.8, and it's a little bit thicker steel. Right here, 2.7, so about where we'd expect to be. We're likely not taking very much lead thread damage here at all. We're probably getting some, which is why we have this larger variation, but we're still able to drive in. What's interesting here is that an induction hardened part only has high hardness on its lead threads. So its lead threads were 45 Rockwell C minimum, but its body threads were equivalent class 10.9. Well, your lead threads are what control your drive torque, but it's your body threads that control the failure torque. So what actually happened here is we had a 1200 megapascal steel, and our fastener body was only about 1000 megapascal. So the steel was actually stronger. So we got a very unusual failure mechanism. We actually stripped the threads off of the fastener itself, off of the male part. And that's why we're starting to look at this different heat treatment called OS tempering. It does require a different steel alloy, but it is still cheaper than induction in the end once you add all the processing costs in. The benefit is it allows us to get our whole fastener up to 50 to 55 Rockwell C. And because it's a different microstructure than an induction hardened part, it's less susceptible to hydrogen embrittlement. But we're hoping that'll drive up our strip torque. That part's currently running through our plant right now, so we'll have that data soon. But our strip torque here is so low actually because our body threads failed. So when we have that OS-tempered part where our hardness is now higher than our mating material, this should jump up to around, we're guessing, 7.5 to 8 newton meters, which means this installation window starts to look a lot prettier. It's still usable right now, but you only have about 1.5 newton meters of range for your tightening torque. So in summary, Rolok HS is a new thread forming fastener. We just started releasing it this year. It is resistant to thread collapse because it uses that compound angle thread where that top angle changes our loading from bending into compression. So even if we do compress the thread a little bit, it still drives. It does reduce the installation end load simply because the threads aren't failing. So when you start to bend those threads over on a traditional thread rolling screw, you have to push really, really hard to get it to go through the part. We don't have to do that because our threads aren't rolling over and bending. We're still serviceable with standard machine screws, but the big takeaway I'd like you guys to take away from this presentation that Rolok HS has really expanded the limits of what we can do with thread forming in high-strength steels. Now, depending on which customer I talk to, I'll hear different general rules. I've heard some things as low as we won't thread form into any screw above 450 megapascals, all the way up to we won't go past 1,000. And you saw the one customer application where we were at DP 980, and that traditional thread rolling screw wasn't really working very well there. But Rolok HS is showing much more promise and could certainly work in that application. So we've really pushed that limit, where I'd say on our end, we'd say the old limit was probably right around 600 to 700 megapascal. So if you asked me when I thought thread rolling fasteners stopped working before Rolok HS, we'd tell you right around 600 to 700, and a lot of that's dependent on your tooling. Certainly didn't work in 1,000, but with Rolok HS, we're all the way up at 1,200 right now. So we've added about 500 megapascals worth of strength that you can now thread form into. And with these new OS-tempered screws that will be coming out in a few months, we might be able to push that all the way up to, we're hoping, around 1,400 or 1,500. Obviously, when you get up to steels that strong, they tend to be very thin, so you have to have some way to increase that thread engagement so that we can get a good joint. Whether that be piercing or flow drilling, either one is fine. And then finally, Rolok HS is available in all common heat treatments and platings. As mentioned, we didn't want to add cost by changing the alloy if we didn't have to. We didn't want to change the heat treatment, so we changed the thread design. But that thread design works with all common platings and heat treatments, which is what we've tested it with. Finally, we'd like to thank the Auto Steel Partnership. They supplied some of the steel plates for the development of Rolok HS. We would also like to thank our customers who requested a thread forming solution for these high-strength steels and worked with us through the development of Rolok HS. And finally, we'd like to throw out an invitation to everybody watching. We are actually getting ready to do a very large round of testing, which we're going to publish in a technical journal, a peer-reviewed journal. And we're open to any materials that you may want to test. So if you have a certain steel that you want, let us know. We're partnered with US Steel. They're going to supply the coupons for whatever steels we need if they have it in stock. So if you need, I don't know, Gen 3 1400, Gen 3 980, or whatever steel you want, let me know. My email's at the bottom, and we'll try to get that data for you. We won't say who the data's for. It'll be just like this presentation. We'll simply say, here's the metal, here's the results. We're going to be looking at drive to failure analysis, which is what you saw today, clamp load analysis, serviceability, and probably some other strength requirements such as pull-out testing, lap shear, and maybe some cross tension. So if you have a certain test you want seen for a certain material, please let us know. We'll do our best to accommodate it, or at least get you something close. If you have any applications you want to discuss, feel free to contact me or go through our website, which is Semblex.com. Thank you very much for taking the time to learn about Rolok HS. I'd be happy to answer any questions. If you have a question after this presentation, feel free to reach out to me. Thank you.
Brandt, thank you very much for an excellent presentation and very impressive videos showing the Rolok in action. I'm going to dive straight in with the first question for you. Is there a big cost differential between Rolok and traditional fasteners?
No. So admittedly, we make most of the traditional thread rolling fasteners here at Semblex. We charge the same amount for Rolok HS as we do for those traditional fasteners. It's the same steel and the same heat treatment, so the only difference is really the roll dies, which isn't a cost increase on our side.
Thank you. Next question. Is Rolok exclusive for automotive seating, or is it applied to other industries like aerospace?
We developed it for automotive seating because that's who came to us and asked for the solution, but it's certainly applicable outside. If you have an application outside automotive, we'd be happy to work with you, happy to supply samples or do testing. Just let us know.
Thank you. How long have you been active in this industry yourself? Same question, how long have Semblex Corporation been active in the automotive seating space?
Sure. So Semblex has been in automotive seating for, I'm going to say, at least 30 years. Admittedly, I've only been at Semblex and in the industry myself for about 3 years, so I'd have to ask somebody to get the exact response for that. But we are heavily an automotive supplier. Most of our business is automotive, and we do quite a bit of work with the major tier seating companies in the U.S.
I'm supposing you can't say who they are, can you?
I cannot at this time.
Is that all NDAs your end?
Yes, yeah. So all the customers that we're working with, it's all NDAs.
Yeah. Okay, thank you very much. Next question. Where was Rolok created?
So the Rolok HS screw was created at Semblex. That was my team that came up with that. It's a Semblex product. It's not licensed from anyone else. It is ours. The original Rolok design, that spiral lobe, is actually a patent that's also owned by Semblex. We didn't create it. We bought that one about 20 years ago.
So with the new Rolok, was it the customers who came to you and said, look, we've got a specific problem here, can you solve it? Or was it more Semblex end saying, right, well, we've got an idea, let's go with it?
So one of the things that Semblex does for our customers is called tech days. So we'll go out if they're requested. Obviously, COVID's a little different right now.
Yeah.
But if a customer wants a little more information on certain screws, we'll send a couple engineers, a couple sales guys out there to give presentations on any topics they may want. One of our seating customers requested one of these tech days, and while we were there, we sat down and discussed, what are some of the problems that you're experiencing, and that's where this came up. They said, well, we've got this HSLA, we've got intermittent failures. Is there anything you can do? And that's what gave us the idea for Rolok HS, because we tested all of our fasteners, and none of them really worked. So we wanted something that would, so we developed that on our own end. On a separate note, if you have any fastening problems and you're looking for a solution, please let us know. We're open to trying to solve as many of these problems as we can.
Are you able to, is it just US based, or do you go globally as well with this?
We can go globally. So Semblex is owned by Jinhap, which is a worldwide fastener company. If there was someone in Europe that wanted it, we would probably work with one of our partners over there and have them make the screw.
Okay. Okay, thank you. Next question. In a service situation with a machine screw, will you have interference with the thread formed by your Rolok HS?
No, there's no installation interference between Rolok HS and the standard machine screw.
Thank you. Next question. I think you've already answered this, but I'm going to ask it anyway. Is Rolok readily available and being used by automotive customers currently, or was it in the concept stage? If it is it available around the world or only in the USA, for example?
Sure. Right now, we are at 2 separate plant trials, so we are actively going into the automotive industry. We should have the results of those in the coming months. Right now, it sounds like it's going to work pretty well, so we should be in full production soon. Right now in the U.S., we have availability of M4, M5, M6, and M8 Rolok HS. Worldwide, we just haven't had a request from outside the U.S. for it yet. We could certainly supply it outside of the U.S. if that was a need.
Okay. Where do you see this in the next couple of years then? Do you think you'd be advancing it, getting it even better?
A lot of that's going to be customer driven. So a customer's got to bring us a challenge, and if Rolok HS doesn't work, we'll improve it.
Yep.
But if it keeps working, there's not a whole lot for us to know on what to change.
Yeah.
Like I said, we're playing with some new heat treatments. We'll probably make some short taper versions, and we'll probably look at some other specific application modifications that we can do. One of the ones we're looking at right now is we know a lot of customers like to fasten plastic to steel, and you need a very, very low drive torque to do that, or you need a way to modify or basically put a torque robbing feature in there that doesn't damage the plastic. That's something we're currently working on. But for the most part, it's all customer driven. If the customer has a need, we'll find a solution.
Well, if it's perfect, why change, eh? Next question. Do you generally do your testing in your own locations or customer factories?
We leave it up to the customer. So for the plant trials we're in right now, we did both. The initial testing was done at Semblex. We showed that data to our contacts. They liked the data, so they wanted the samples for themselves. They did their lab testing, and then since that worked out, it went to plant trial. We can do either one. We do supply testing for free, so long as it's a reasonable amount of requested tests. And like I said, right now we're working on that white paper, so we're definitely open to doing any testing you want for Rolok HS.
Okay, thanks. Next question. I probably missed it earlier. Please, can you go over the key reasons why traditional thread formers fail in these high-strength situations?
Sure. Let me pull up the slide here. All right. So I'm going to play this simulation again, and I'll just let it run while I'm talking. So what happens is, with these traditional thread rolling fasteners, a good portion of the load that's generated when your thread contacts the female material is along the axial length of the fastener, basically meaning it's trying to bend those threads. And what happens is whenever you get high enough of a bending load, the thread starts to bend and then it starts to collapse like you see in this simulation and also like you see on this part down here. So for the most part, the reason is really in the flank angle. Obviously, if you have a part that's a fastener that's way, way harder than your mating material, it'll work. But when you get into some of these higher strength steels, for example, the Gen 3 1200 was 40 Rockwell C hardness. You're not going to get a fastener that's 40 points higher, at least not made out of steel. So you start needing a different solution. Hardness doesn't work anymore. You need to be harder, but you need to reduce that margin that works. So that's where we came up with Rolok HS. It still needs to be harder than the mating material, but it doesn't need to be all that much harder.
Thank you. Next question. So I've got a couple of questions from Teresa. So here we go. Are there samples available for testing in the M6 and greater sizes?
Yes, we have M6 parts in hand right now that we can supply. Our M8 parts are at our heat treat and platers right now. They'll be back in a few weeks.
Thank you. Another question from Teresa. What is the recommended hole sizes and material thickness for the different fastener sizes? And if not, what would you recommend?
So that's application dependent. It's really going to depend on how thick your steel is, how strong it is. If you need specific guidelines for that, reach out to us and we'll review the application and let you know what we would recommend for the hole sizes.
Thank you. Another one from Teresa. What is the timing cost on getting about 100 samples in the M6 size of fastener testing?
We can ship those out today, tomorrow. I mean, they're on hand, so it's not a problem.
So in other words,
Cost
Teresa,
is just whatever shipping you want to pay for. So
they'll be with
overnight
you.
Is fine.
They'll be with you by tomorrow if you need them. Another one from Teresa. Can the lead-in points such as CA point or dog point be added to your fastener design for increased access in the fastener joint application?
We should be able to do a dog point without a problem. CA point we'd have to review. I'm not sure if we could do it with how wide this thread is. We could certainly give it a try. We haven't needed it yet. Admittedly, a lot of the applications that we're replacing at our seating customers, they were CA points. They're finding they don't need the CA point with Rolok HS.
Thank you, Brandt. Next question. At our company, we are looking at various high-strength steels. What material sample size do you need to help us evaluate Rolok HS, and is there a cost for this?
So we'll do the testing for free. And we have our own little punching press to make holes. So either you can make the holes or we can make them. It doesn't matter to us. As far as sample sizes go, we usually like to use strips that are about 1 inch wide and whatever thickness you want. Length, we're pretty open. They can be anywhere between like 3 and 12 inches, and it'll work just fine. But if you have any specific steel you want, specific application, feel free to reach out to me, and we'll get something figured out.
Okay, thank you, Brandt. Next question. What screw sizes are these Rolok HS fasteners made in?
So right now we have an M4, an M5, an M6, and an M8. If we have a request, we might make an M3. As of now, we haven't had a need to make anything bigger than an M8, but it's certainly scalable. If someone needed it, we could have it made.
Okay, great. Next question for you. Do you have any information on testing M8 fasteners?
No, we haven't tested the M8s yet. Like I said, they'll be back in a few weeks. That's all going to be published in the white paper or the technical journal that we'll probably put out at the end of this year. So right now, we really want to hear from our customers. What materials do you want tested so we can include all that data?
Thank you. Next question from Dimitra. What is the maximum starting angle of misalignment? Are there different screw tips available for increasing this angle?
So we are, just like most traditional thread formers, we're able to go 10 to 15 degrees off angle and still drive in. Admittedly, we haven't tested anything further than 15 degrees. We could certainly give it a shot. We do have a short taper screw available and a long taper screw available. The long taper would deal better with off-angle drives. But we have not tried, as mentioned, a CA point or any other specialized points yet.
Okay, thank you, Brandt. Next question. Can these be driven with a normal electric screw driving system?
Yes, any system that you're using for a traditional thread rolling fastener will work for Rolok HS. We're right about the same torque ranges that you'd expect, so it should be no problem. Admittedly, in our lab, we use Atlas Copco drivers. You could use those or anything like them.
Okay, thanks, Brent. Okay, well, final question. As you zip through 17 very quickly and brilliantly, has testing been performed? Oh, we've got another one. Has testing been performed driving the fastener in the opposite direction of the punch? As this is a typical issue in installing traditional thread rolling screws.
Yep, let me get to the slide real quick. All right. So the answer is yes. So if you look very closely at these videos here, you see this nasty little blowout in the back? That's the punch exit side. So actually all these screws were driven through the punch exit side. Because as you mentioned, that's where our customers were having the problem. So that's where we targeted Rolok HS, which you'll see on the right side going through that punch exit side without problem. The punch entry side is very easy. We don't have any problems there either.
Great, thank you. Okay, a final question from Teresa again. Can the Rolok fastener be made with using fine threads such as M10 times 1.0 or M10 times 1.25 or 7/16?
We would have to look into it. We haven't tried. My gut would say probably not, because the way that thread's going to scale is not going to work very well, but we could certainly give it a try.
Okay, that's brilliant, Brandt. Thank you very much. I just want to finish on, somebody's written for Hugh's written, very good presentation, graphics and videos especially, so thank you very much. Ladies and gentlemen.
Thank you, everybody. Thank you for the questions.
Thank you, Brandt. Ladies and gentlemen, Teresa just said, excellent presentation, thank you. Ladies and gentlemen, I would like to say a big thank you to Brandt from Semblex today for an excellent presentation and some very impressive videos. Today's webinar will be on demand for you to rewatch. Once again, thank you to everybody for attending, and a big thank you again to Brandt from Semblex. We do look forward to seeing you all at our next We Automotive webinar. Thank you all and goodbye.